So can anybody tell me why the general purpose processors are not suitable for DSP applications? Can anybody summarize? Okay. So as we know, many of the DSP algorithms, all the DSP algorithms uses accumulation of multiplicative products. Okay, a series of multiplications will be carried out and those will be accumulated. Okay, which needs lots of number crunching operations, right? And that has to be completed within the time constraints, within the specified time constraint. Most of the DSP systems are real-time in nature. See, examples, see, we are talking in a phone, right? So the signal processor involved in the phone, it has to accept the speech signal and then convert into digitize and then transmit it. Okay, at the receiver, if there is any noise involved in it, it has to be denoised by the processing algorithms, which are nothing but the filters, and then convert back to analog domain and then given to our speakers so that we can listen, right? So almost all DSP signal processing applications are of real-time in nature, need to obey the real-time constraints. So mostly we have anyway two types, soft real-time and hard real-time constraints. Whatever it is, it has to obey the specific time constraints. Okay. So the architecture which is available for microprocessor is not at all suitable because it doesn't give the specific time constraint, and the processing unit which is available in GPP is not at all sufficient for DSP applications in a way where it involves all the overheads. Okay, we have loop overhead, address generation overhead, right? There are no specialized addressing modes that are suitable for DSP applications. Okay, and we can extract the same memory is used for program and data. Okay, we have only single bus, which is address data, and system bus is single address data and control, which is meant to access either program memory or data memory. Okay, so with this single bus, either you can read a program or we can read data only at one at a time. Okay, we can't do both at a time. Okay, so to get the output in a specified time constraint, we should modify the architecture of GPP, which has to be suitable for DSP applications. So that architecture is nothing but which is developed by your Texas Instrument manufacturer or else analog device. Okay, so the architecture is quite varied. So many changes are happened to facilitate the DSP algorithms basically. Okay, so that is the summary for differences between general purpose and DSP processor. So in today's session, we will see the data formats, number formats, fixed point, floating point, and block floating point, and of course IEEE 754 floating point and Q notation. These are the different formats. Okay, so we will see those formats. So why we are seeing these number formats? Because anyway we are dealing with the numbers, right? So in any digital signal processor, as in like your microprocessor or any digital system, so here my signals are represented as numbers starting from the input and anywhere through different stages of processing, and finally the output. Everything, the signals here are represented with the help of numbers, right? So here not only the signal, if your application is dealing with the filters, so the filter coefficients are also certain numbers. Okay, so of course depending on the range range of signal values or quotient values, you have to choose one particular number format. Similarly, based on the number format, there will be a complexity involved in performing the operations or it also. So what should be the hardware complexity and also other speed requirements. Okay. So those are also varied with respect to the number format. Okay. So let us look at some of the typical formats that are used for representing the signals as well as the positions in DSP systems. The first format is a fixed point format. Of course, these seems to be familiar to you topics, but we will go little in detail here. Okay. Fixed point format. So can anybody describe this fixed point format? Correct. Fixed point format. Fixed point format. What is the definition of it? Can anybody say? Why it is fixed point format? See, we are dealing with numbers. See here, anyway, the numbers can be positive or negative, and the numbers can be integers or fractions or integer fraction numbers, right? A combination of it, right? So here, whatever it is the number that will be stored in a fixed number of bits when we come for a processor, right? The registers are a memory bit, they are fixed. So to store my number in a specified fixed number of bits, okay? So what is the position of the decimal point will says whether the format that is used is a fixed or floating point. If the decimal point is fixed at one place, it is said to be the fixed point format. And if it is varied, then it is said to be the floating point format, right? So these topics anyway, which are familiar, we'll go in detail. Fixed point format. Here my decimal point is fixed at particular position. Okay. So usually there are two ways, right? Two different formats are used under fixed point. Two different numbers we can represent. That is integer representation. Only integers can be represented, or only fractions can be represented. Okay. See, if I take an n-bit number, so it will be having, it means I have n bits, which is varies from 0, 1, 2, 3, likewise, I'll be having n bits. So this, if I say this is as n minus 2, and this will be n minus 1. So totally 0 to n minus 1. This is my n bit number, if I suppose. Right. So for this n bit number, I have a bits B0, B1, B2, B3, B4, and so on. I'll be having last bits Bn minus 2 and Bn minus 1. These are my bits, actual bits, which can be either 1 or 0 that have your value of the particular value, right? Okay. See, in this n bit number, if my decimal point, whatever it is, if it is fixed at one position, that's what fixed point format. In this, we have two different representations, integer and fractions. In integer representation, my decimal point is fixed at rightmost of the LSB, after LSB. So this is what called LSB, right? LSB bit, least significant bit, and this is what called MSB, most significant bit. right? So if my fixed point is fixed at here, if my decimal point is fixed at here, okay, see my decimal point is here, then it is said to be the integer representation. We are going with integer representations because my decimal point is here. I can represent, I can take all the bits participated in magnitude in terms of integer, right? Am I clear? So this is one format which is called integer. See, in integer representations, again, I may have both positive numbers and negative numbers. Okay. In integer numbers, in integer representation, where I may have my numbers both positive and negative, right? So I can go by this, whatever it is there, the most significant bit, right? In positive and negative means my numbers are of signed, then this most significant bit widely used for representing sign. Okay, so this bn minus 1 can be treated as a sign bit. Okay. And of course, usually we go by 2's complement representation for storing the numbers anyway. Okay, so the most significant bit usually represent the sign bit, and if this bit is 0, it means my number is positive for positive numbers, and this is 1 for negative. Okay, so if so, now I have to know what is the range of values that I can represent with this format. Okay, where my decimal point is here in integer fixed point representation. This is what called integer fixed point representation. Integer fixed point. In this, I have to know what is the range of values that I can represent by using these numbers. Okay, so range of values. The range means what is the minimum and maximum value that I can represent. So I should have a minimum value and I need to calculate now the maximum value. Okay, so these two values I wanted to calculate, right? So now can anybody tell? It is simple, just an n-bit number and signed case, right? Most significant bit is S and remaining all bits can participate in magnitude. If it is so, what is the minimum and maximum range of values? See, for a simple, you can take just 8-bit case for flexibility. For 8 bits, 0, 0, 0, 0, 0, 0, 0, 0. 8 zeros, right? This gives you the minimum number, right? Which is nothing but 0 in decimal, and maximum number 8 ones. This gives you 255 in decimal, right? But here I am treating all the bits as participated in magnitude. All are treated as a positive numbers, but this is not I want, right? So I have both positives and negatives. In that case, I will go by 2's complement form, and I can take the most significant bit as a sign bit, and I can calculate what the range of numbers in 8-bit case, which is nothing but minus 128 to plus 127. Do you remember this range? Minus 127, sorry, minus 128 to plus 127. This is in case of 8-bit. Similarly, in case of 16-bit, if you want, that is minus 32762 plus 32767. How we get these values? How we get these values? It's simple. Minus 128 means if it is n bits, then I can write this as minus 2 power minus, how can I write as minus 128 minus, since we are taking it is 8 bits, minus 2 power n minus 1 2 plus 2 power n minus 1, isn't it? Okay, so where n here it is 8 In case of here, n is 16. Okay, so how can I get this value? Do you know the range of numbers in 8 bits? Do you remember this? Is it clear, or else you want me to derive? Anybody, please respond, ma. Is it no? Is it clear? I mean, this expression is very familiar to you. The range of numbers represented by n fixed point integer values. See here, see if these are my n bits, how can I calculate its magnitude for any x? If let us suppose for positive number, treat this as 0, then I can go by the expression called b naught b0 into 2 power 0 plus b1 into 2 power 1 plus and so on b n minus 2 into 2 power n minus 2. Okay, and signed bit is 0 for positive case. This is only the expression. For negative case, I will be having my sign bit s as 1. Then my expression is changed to, this is all the value, and minus 2 power minus s 2 power n minus 1. Okay, if I have s as 1. So I don't know whether s is 1 or 0. So then I can write this as minus s into 2 power n minus 1. This is what the value of a number x with n bits in a fixed point integer can be represented. Okay. So to have, this is what the value to have a minimum number negative, in the negative maximum case. Okay, in negative maximum case, negative, so s bit is 1 and all the bits. Since I want a maximum, the magnitude should be in a negative case. Negative maximum number I want. See, which is negative, sorry, I should have negative minimum, right? Negative minimum, the magnitude should be maximum. Okay. So what can be the value, bit values? So where all these bits negative, so s bit will be 1. S bit will be 1. And I want a minimum number who in negative case, the magnitude is maximum, right? If magnitude is maximum in a negative case, the number behave as a minimum number. So to have a maximum magnitude, I should have all zeros here. All are zeros. Then I'll be having negative minimum. Okay. So for this case, if I supply these bits in these values, in this expression, okay, in this expression, what happened? All are zeros except this value. So s is 1 minus 2 power n minus 1 I'll be getting. Am I clear? This is the negative minimum. If I want positive maximum, so what can be the values? Positive and maximum. So all should be 1. All should be 1. So if I supply those values in the same expression, so b naught, b1, all are 1s. So 2 power 0 is 1. 1 plus 2 plus 2 square plus and so on. 2 power n minus 2 and s is 0. There is no expression here. Right? 2 power s is 0 here. So this term we will lose. This is what the final value. So I can write this as 1 plus 2 plus 2 square plus and so on to power n minus 2. How can I write this? Just tell me, how can I write this? By using the formula, series of expressions, 2 power 1, 2 power 2 and so on. Please respond, ma. Simple value, simple expression. All values are ones, right? So I can write this as 2 power n minus 1 minus 1, 2 power n minus 1 minus 1. Yes, please respond. You can take a simple range for take n as 8 bit. So for n 8 bits, the range of values is minus 128 to plus 128. So if I replace n by 8 minus 2 power 7, 2 plus 2 power 7 minus 1, which is nothing but minus 128 to plus 1. Similarly, replace n by 16. Okay, we'll be getting the values, right? So finally, what is the conclusion? For fixed point integer representation, for n bits, if my number is having n bits, any number in x can be represented in this expression b0 into 2 power 0 plus b1 into 2 power 1 and so on, bn minus 2 into 2 power n minus 2 minus s into 2 power n minus 1, where s is the sign bit, most significant bit represent. So in this case, the range of values that I can represent is minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. So this is the range of signal values allowed for n bit fixed point integer representation. Okay. I think I'm clear. See, my dear students, please respond. If you are not clear, we'll see an example. Else I can move further.
Clear, ma'am. Yeah.
Okay. So this is about fixed point integer representation, where my decimal point is after the LSB. My decimal point is here. After the LSB, if my decimal point is there, then that is called integer representation, where we can represent only the integers. For n bits, this is what the dynamic range, sorry, just range, minimum and maximum values. Okay, minus 2 power n minus 1 to 2 power n minus 1 minus 1. Okay, for 8 bit, these are the values. For 16 bit, likewise, you can go ahead. Okay, and next we'll see the other representation, fractional representation. In fractional representation, in fractional representations, we'll be having our decimal point. We'll be having our decimal point after the most significant bit. Okay, after the most significant bit here. Okay, since MSB, it says about the whether the number is positive or negative. So my implied binary point is here. This is where my decimal point exists. Okay, and it is fixed here. Right? See, for example, if I have a number like this, so 0.1110. Okay, how can you calculate its corresponding decimal values? How can you calculate its corresponding decimal value? You have to apply powers of 2, right? So what is the power of 2 here? 2 power minus 1, isn't it? 2 power minus 1, 2 power minus 2, 2 power minus 3, and so on. Okay. So where my numbers are here, we can adjust for fractional representation. This is signed bit out of all numbers n minus 1 to 0. Okay, this is signed bit anyway, and this is corresponds to bit minus 1 and bit minus 2, bit minus 3. Likewise, how many numbers we'll be having? We'll be having bit n minus 1. Okay, so this is 1 bit completely n bit numbers. So how here my decimal point is at this position. Now what is the expression for x value here? My any number x can be written here as, this is s is the sign bit, right? So which is nothing but minus s into 2 power 0 minus s into 2 power 0 plus b minus 1 into 2 power minus 1 plus b minus 2 into 2 power minus 2 plus b minus 3 into 2 power minus 3 and so on. B n minus 1 into 2 power minus of n minus 1. Am I clear? So this is the expression for x value in fractional representation, where my decimal point is a fractional fixed point representation, where my decimal point is fixed after MSB. Okay. So now in this case, I have to now calculate the range of values that I can represent here. Okay, the minimum and maximum. Both it involves positives and negatives based on the S value. Okay, right? So this is our fractional value, X value. Now I have to calculate minimum and maximum. How can I do? Let me erase everything. Okay. So now I want to calculate the minimum value, minimum negative value. Let us suppose minimum negative case. Let us go by the 1, 1, 1. Let us suppose I have all ones. So what this value it will give, we just calculate. See, I have n ones. Substitute this in this expression. What is the value that I am getting? Minus 1 plus b minus 1 is also 1. All are 1, right? So minus 1 plus 2 power minus 1. I can write that as 1 by 2 plus 1 by 2 square plus 1 by 2 cube and so on. 1 by 2 power n minus 1. Am I right? Okay. So I'm having minus 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus and so on. 1 by 2 power n minus 1. See, if you have an expression like 1 plus a square plus a cube and so on plus a power n minus 1. I can write that as 1 minus a power n by 1 minus a if a is less than 1, right? So I can write this as 1 minus a power n by 1 minus a only when a is less than 1. Which expression I can write? 1 plus a square plus a cube and so on, a n minus 1. Okay, this expression I can write like this. So I can simplify here. My a is 1 by 2, which is less than 1. So to replace like this, I should have 1 plus. So I'm adding 1 and subtracting 1. Okay. So this is minus 1 and minus 1, which will produce you minus 2 and this expression. So 1 minus half whole power n by 1 minus half and minus 2. So what is this value? This is 2 into 2 power minus n. I'll be getting 2 cancelled. So finally, this is a half, right? This is half. This 2 can go here. 2 into 1 minus 2 power minus n and minus 2. This 2 and this 2 can get cancelled. So I'll be getting minus 2 power minus n plus 1. Okay. Or else I can write this as minus 2 power minus of n minus 1. Okay. So See, minus of 2 power minus n minus 1. So which is nothing but minus 1 by 2 power n minus 1 minus 1 by 2 power n minus 1. See, 2 power n minus 1 is the bigger value, which is 1 by, so it is very less value, and for that we have a negative symbol. So this can be considered as negative. In negative case, maximum, okay, right? But I want negative minimum. So obviously 1 for all ones, if I am getting negative maximum, so I can get negative minimum with 1 with all zeros, right? So take 1 and all zeros, n number of zeros. So my x value here it is, since here MSB is 1, so my S is 1 and remaining all are zeros. So minus 1 and all are zeros. So this is minus 1. So out of these two, which is the least value, minus 1 or minus 1 by 2 power n minus 1? See, if I take n, let us suppose 2 bits, n2. 2 minus 1, 1. So 1 by 2 is minus 1.5, right? Which is the least value, minus 0.5 or minus 1? Minus 1 is the least value, right? So we got our negative minimum. Okay. So this we got. The least value that I can represent is minus 1. That we got. Now I should have a positive maximum. So to have positive maximum, this bit will be 0 and all are 1s. Okay. So this is 0 and all are 1s. I'll be getting, so S bit is 0 and all are 1s. So the same expression, but we don't have this. So this will be minus 1. Okay. So I'll be getting 1 minus 2 power n minus 1. Okay. So this is 1 minus 2 power minus of n minus 1. Okay. This is the range of values in case of fractional fixed point representation. Am I clear? So this is the positive maximum that I can represent. Range of values is minus 1 to 1 minus 2 power minus of n minus 1. Fractional fixed point representation. When we come for integer fixed point representation, the range of values is minus 2 power n minus 1 to minus 2 power n minus 1 to 2 power n minus 1 plus 2 power n minus 1 minus 1. Right? This is fixed point and this is integer and fraction. Okay. So I feel it is clear. Let us see few example. My question is, so here my question is, what is the range of numbers that can be represented in a fixed point format using 16 bits if the numbers are treated as signed integers, signed fractions. So this is the problem. What is the range of numbers that can be represented in a fixed point format using 16 bits if the numbers are treated as signed integers and signed fractions? Okay. So we have already calculated for n bit fixed point. sorry. So we have calculated for n bit fixed point integer format. The range is 2 power, sorry, minus 2 power n minus 1, 2 plus 2 power n minus 1 minus 1, right? So these, in terms of writing in n, feels you difficult, but it is known expression only, right? So it is minus 2 power n minus 1, 2 plus 2 power n minus 1 minus 1. This is what the range of values for fixed point integers, right? See, whenever it is 8-bit, I have to replace n by 8. But what they asked for 16-bit. Just replace n by 16. So I'll be getting minus 2 power 16 minus 1, 2 plus 2 power 16 minus 1 minus 1. Okay, so which is nothing but minus 2 power 15 2 plus 2 power 15 minus 1. So it is minus 2 power 15 is 3 to 7. How much? Sorry. I can use the calculator here for easy. Two power 15. 32768, same, right? So minus 32768 plus 32767 that we have already seen. Okay. So this is the range of numbers that I can represent in a fixed point signed integer format. Okay. Now I have to go with the second problem, signed fractions. I feel integer fixed point is clear. Now let us go by signed fractions. So in case of signed fractions, what is the range that we have calculated just now? The range is fractional values. So minus 1 to 1 minus 2 power minus of n minus 1. So this is for n bit fixed point fraction format, the dynamic range, sorry, the range, not the dynamic range. Okay. So for n bit fixed point fraction, this is the range minus 1 to 1 minus 2 power minus of n minus 1. Now just replace n by 16 here. So it is fixed minus 1 to 1 minus 2 power minus 16 minus 1, which is nothing but 15. Okay. So minus 1 to 1 minus 1 by 2 power 15. Okay. So if I calculate this, it is approaches to 1, but not exactly 1. So minus 1 to 0. You calculate using calculator, I'll be getting 0 0.9996948. Okay. So this is a range of fractions that I can represent between minus 1 to plus 0.999. You just observe all are fractions only. Minus 1 to 0 and 0 to 0.999. All are fractions. Only fractions I can represent with the help of where my decimal point is after most significant bit. Okay, this is the range of values for signed fractions, and this is the range of values for signed integers. Okay, so you try to practice how to calculate these values, and also the formulae for fractional and the fixed point range of values. Okay, so you can derive this, you practice that, right? This is about fixed point representation. Of course, by observing the fixed point itself, it says that the number of bits are fixed, the number of bits anyway they are fixed, and even the decimal point here is also fixed. Okay, so in most of the DSP implementations, we may have additions, subtractions, multiplications, right? So widely we come across multiplication and successive cumulative accumulating the partial products will come across, right? So multiplication of integers, we know they produce obviously the numbers which may require more bits to represent, right? That the product will be obviously the double width of the inputs, right? They require more number of bits to represent. And if I go with only the fixed point, fixed number of available bits, of course, what is the condition that we may arrive? That's what called a wraparound condition, right? So it is clear that there is a possibility of obtaining the wraparound condition whenever we fix the number of bits used for representing any number. Okay, because see, for example, we are using both signed and positive and negative numbers. So signed numbers we are using. We have a number like minus 128 for 8-bit case. Minus 128 is the least number. And if I want to subtract again 1 from it, minus 1. See, I have minus 128. See, minus 128. I want to subtract again one more 1 from this. Okay. So I'll be getting minus, I should get minus 129, which I cannot represent with the available fixed number of 8 bits. So then what is happening? It will wrap around. Means minus 128 is this 1 0 0 0 0 0 0 0, and minus 1 is 8 ones. So if I add this, this will get here 7 ones and 1 0. So this is anyway carry. This is what we'll be getting. What is this? This is plus 127. Okay. See, we have minus 128 here and plus 128 7 here. This is the way that they are representing minimum to maximum. Okay. So if any operation is done on this number, which has to produce lesser number than this, but we are getting a number which is greater than this, which we are not expecting. That means the result is wrap around. It starts going from higher numbers also, wrap around. This is the same case for even the positive numbers. If 2 more positive numbers, if you add, whose result is unable to fit into the specified number of bits, then it goes to the negative range. Okay, it means wrap around. A circle thing is happened. That's what called wrap around condition. So what is doing wrap around means it generates the most negative number after the most positive number, or else it generates most positive number after the most negative number. Okay, am I clear? Please follow my words. Wrap around generates the most negative number after the most positive number. Okay. In our example, we have taken an example of adding minus 1 to minus 128, right? So this is the most negative number, right? After most negative number, we are getting a most positive number. Okay, so it is wrapping around either of the cases. So wrap around generates the most negative number after the most positive number, or else most positive number after the most negative number. Okay, vice versa, right? So this is what called wraparound condition, which exhibits more in fixed point in formats where the number of bits are fixed for representing your numbers. Okay, so to avoid this problem, widely we go by a fractional point representations. Okay, so in case of fractional representation, whenever 2 fractions are multiplied, it is obvious that we may result a fraction which is smaller than the earlier ones. Okay, smaller than the original fractions. Of course, I can have a proper value by discarding the least significant bits anyway. So that is the advantage of going for representing a numbers in fractional way, signed fractions. Okay, right? So this is about a fixed point representations and its advantages in integer and in fractional ways. Okay. And the dynamic range is completely depends on the number of bits. Okay, right? See, for a 16-bit case, this is the value, and for 16-bit fractional case, this is the range. See, still, if you want to increase the range of numbers that I can represent in fixed point, so one simple and obvious approach is to increase its size. That is only the way, right? So rather than going for 16 bits, if I want to increase my range of values, then I obviously have to go by 32-bit range. I can have a much more more number of values I can represent, right? So we are nothing but doubling the size. So if the size is doubled, the range of numbers will obviously increase, right? So it is not just simple for doubling the size. Still it creates some problems, like say, we know whenever we talk about memories of byte memories, if I 8-bit, I have a less dynamic, less range, then I want to go by 16-bit representation. Then the memory could able to store, it has to store my number, 16-bit number in its memory with the help of 2 successive memory cycles, because each time it can store only 8 bits, right? Okay, so just simply doubling the size, and still if you use the same fixed point format, okay, which we call that as double precision fixed point format, but it adds other disadvantages, like it requires double storage for storing your number, and also to read the same data it may need double the number of memory accesses, okay, for the same size of DSP bus, right? Because we are extending the number length to 2n rather than n, doubling the size. So 2 cycles I require more for reading the complete data item. Okay. So simply doubling the size will not only increase the range, but it doubles the requirement of storage as well as the number of accesses. It doubles the memory accesses also. And of course, the computational complexity, of course, anyway, it increases as the number of bits are increased. Okay. So that's what double precision fixed point format, where we are increasing the number of bits to double, that will increase the range of values, but in another aspect, it will double the requirement of storage as well as double the memory access, of course, the complexity also, right? So that is about double precision fixed point format. Okay. And now this is for about a fixed point. In next class, we'll see floating point format. Is there any doubts here? Please let me know. You need to derive the expression for minimum and maximum range of values in both the cases, signed integer and signed fractions, and practice problems based on the number of bits. What is the range? Okay. And what are the advantages and disadvantages of integer signed fixed point format, where a wraparound condition may exist, which can be eliminated by using signed fraction representation. Okay. Still, to improve the range, we are going with double precision fixed point format. Am I clear? So next class we move to floating point format. That's all for today. You can ask if you have any doubts. Meanwhile, I will collect the attendance. I'm just noting down the numbers those are presented. Once the elective list is fixed, I will call the numbers. Dinesh Reddy, tell me your roll number.
Ma'am, it's 17 batch 115, ma'am.
17 batch 115. Can you please change your name with roll number?
Yes, ma'am, changed it.
Okay, thank you, ma'am. Okay, ma'am, that's all for today. I'm ending the meeting. Thank you.
Ma'am, 17 batch 88 present, ma'am.
Yeah, I have taken from the list. Present only.
Okay.
20. Fine, thank you.